All right, so this video is going to focus on acid and base reactions that result in gases being formed. There are four gases that we typically can see form, three between acids and ionic compounds, and one between a base and an ionic compound. They can make CO2, H2S, SO2, and NH3. So if we have a metal carbonate or bicarbonate present, that's the vinegar and baking soda reaction that you probably saw with volcanoes when you were younger. They will make an ionic compound as well as carbon dioxide gas and H2O. When you have a metal sulfide react with an acid, you will make a metal salt and hydrogen sulfide gas. When you have a metal sulfite react with acids, you'll make an ionic compound as well as sulfur dioxide and water. And then finally, when you have an ammonium salt react with a strong base, you'll make an ionic compound as well as ammonia and H2O. How the gases are able to form is that basically in all four of these examples, you have a double replacement reaction taking place. And in the three where the anion contains oxygen, that acid or base that forms is able to immediately break apart into the gases that you see there, and water is generated. So here we have solid nickel 2 carbonate that's treated with sulfuric acid. So to write the formula between nickel 2 and carbonate, we're going to get NiCO3. That's going to exist in solid form. Sulfuric acid is coming from sulfate. Sulfate's -2. We know that acids are aqueous, so that's going to give me H2SO4. We have a carbonate with an acid. We know that a salt's going to form, so those are going to be the combination of the nickel and the sulfate, NiSO4. Sulfates are soluble, and as long as they're not paired with calcium, barium, strontium, lead, silver, or mercury, so we're good to go on that front. And then we have H go off with CO3, which would normally make H2CO3, but H2CO3 immediately separates into carbon dioxide and water. Carbon dioxide is a gas, water is a liquid. So at this point, if I look, my equation appears to be balanced. I've got one Ni on both sides. I've got one carbon on both sides. I can't do carbonate this time since I don't have carbonate on the right side of the equation. I have two hydrogens on both sides. I have one sulfate on both sides. So now if I look at the remaining oxygens and CO2 and H2O, I have three there, and I have three in carbonate. So we're good to go on balancing. Again, I need to focus on the aqueous substances to determine if they can dissociate. I know nothing else is going to be able to do it. You're not going to have equations with liquid metals. They don't exist at room temperature, other than mercury. And the only time you're going to see mercury that I can recall is in an ionic compound. So don't worry about it. So the nickel carbonate stays together. Sulfuric acid is one of my strict 6 strong acids, so it's going to dissociate into its ions, hydrogen ions and sulfate ions. We already said that nickel 2 sulfate is soluble in water, so that too is going to dissociate into its respective ions, and the CO2 and the water are going to stay intact. So if I look at that complete ionic equation, I see that I have sulfate ions on both sides of the equation, but that's the only ion that remained unchanged. So that is my spectator ion, and the remaining components would make up my net ionic. In example B, we have ammonium chloride, a solution of that combined with aqueous lithium hydroxide. Those are two ionic compounds. So if I follow my rules for writing formulas between ammonium and chloride, I would get NH4Cl plus 1 and minus 1. It's a solution, so I know it's aqueous. Lithium hydroxide, again, following my rules for writing ionic formulas. Lithium's plus 1, hydroxide's minus 1, and you were told it was aqueous as well. Again, these reactions are going to look like double replacement reactions, but because you have the strong base paired with an ammonium-containing compound, we're going to make the lithium chloride, but then ammonium and hydroxide would come together. Ammonium hydroxide can release water, and it also gives off ammonia gas. So ammonium hydroxide splits into ammonia and water. We just saw with the previous example, carbonic acid splits into water and CO2. Again, the three aqueous compounds are the ones I need to focus on to determine if they dissociate. We know all compounds containing ammonium do. We know all compounds containing alkali metals do. So the lithium compounds are also going to dissociate into their respective ions, but the ammonia and the water are not. So in this particular example, we do have a couple of spectator ions. Both chloride and lithium remained unchanged. So in our net ionic, we would just show the ions that were left on the reactant side and the gases that they formed on the product side. This time we have an acid and it's paired with a compound containing sulfite. Sodium sulfite in aqueous form is mixed with acetic acid. So ionic compounds balancing out our charges. Sulfite is SO3 minus 2. Sodium is always plus 1. We need two NAs, Na2SO3. We're going to mix that with acetic acid, which comes from acetate. Acetate's a minus 1 ion, so add a hydrogen to it and you get acetic acid, HC2H3O2. Again, the cations switch places. Sodium's going to go hang out with acetate. Na's plus 1, acetate's minus 1, so we take one of each of them. All acetates are always soluble. All alkali metals are always soluble. And we're left with hydrogen and sulfite. And that would make sulfurous acid. Water can come out of that, and that leaves behind sulfur dioxide gas. This equation does require some balancing. We have two NAs on the reactant side and only one on the product side. And when we do that, our sulfurs are already balanced. We're going to hold off on oxygen for a second, but we did need to balance the acetic acid on the reactant side because we have two acetate ions now on the product side. By balancing the two acetic acid molecules on the left side with the acetate on the right, that gives us two hydrogens, which balances out with the two H's in water. We have three O's that were remaining in SO3, and we have two in the SO2 plus one in the H2O. That also gives us our three oxygens. Again, the aqueous components are what we need to focus on, whether or not they can dissociate. Sodium sulfite contains an alkali metal, so that absolutely will break apart into sodium ions and a sulfite ion. But acetic acid is a weak acid, and weak acids do not fully dissociate in the presence of water, so we do need to keep that one together as a unit. Our sodium acetate compound on the product side is an ionic compound. It has an alkali metal as well as acetate ions, so it is going to dissociate. Keeping in mind we need two of each ion since we had two molecules of NaC2H3O2 present. Our gas and our water remain unchanged. So looking at both sides of my equation, I see that I have sodium ions on both sides. So those are going to take care of each other. That's going to be my spectator ion, and I will be left with the remaining reactants and what's left of my products to make up my final equation. And I also want you to notice in this particular example, and I know we've probably seen some others like this, but there is a net charge on both sides of the equation, but it's the same charge. So we do need to be balanced by atoms, but we also need to be balanced by charge. We have an overall charge of -2 on the reactant side with sulfite, and because we have two acetate ions on the product side, we also have a charge of -2 there. Our final example is going to be between potassium sulfide crystals and nitric acid. Again, ionic compound, you've got an alkali metal to get started, balance out your charges, you get K2S. We're told it's a crystal, so that's why you see the S written after it. Nitric acid is coming from nitrate, which is -1, so HNO3, which is going to be aqueous. Potassium and hydrogen switch places, excuse me. So K goes off with NO3 to make potassium nitrate. Alkali metals are always soluble, nitrate metals are always soluble. You know you have water present, so that's going to dissociate as well, or sorry, stay in aqueous solution. And then the hydrogen goes off with sulfur. There is no oxygen this time, so the only thing that gets made in that particular product is the gas, hydrogen sulfide. Complete ionics, again, are just going to be your aqueous solutions that are either made from ionic compounds or strong acids. The first aqueous solution, HNO3, is a strong acid. The second aqueous solution is a soluble ionic compound. So they are going to separate. Sorry, I forgot about balancing, my bad. Let's go back there for a second. You have two Ks on the reactant side, so you need two Ks on the product side. When you get the Ks on the product side, that gives you two NO3s, so you need two NO3s on the reactant side. You had one sulfur on both sides, and now you have two H's on both sides. All right, back to our regularly scheduled programming. K2S as a solid cannot dissociate, but HNO3 as a strong acid can, and because there's a coefficient of 2, it will make 2 of each of its ions. KNO3 is an ionic compound. There are 2 units of those, so that 2 will dissociate, while H2S will remain intact. If I look at my complete ionic equation, I see that I have nitrate ions on both sides, so those are going to cancel out. But that is the only ion that is going to act as a common ion, as a spectator ion. So you're going to be left with K2S and 2H plus makes 2K pluses and H2S.